Welcome, pre-calc honors students, to 13-.3 Arithmetic and Geometric Series and their sums. And our objective is to find the sums of the first n terms of arithmetic or geometric series. So the key word here is series. Series actually means the sum of the terms in a sequence. So notice the difference between sequence versus series. 2, 6, 10, 14 versus 2 plus 6 plus 10 plus 14. And those are finite series, where you actually end after a certain number of terms. Infinite series we'll look at in the next section, where you might have a bunch of terms that you're trying to add up. And this really only makes sense when we have a converging series, and we'll talk more about that later. For right now, the explicit definition of S sub n is t sub 1 plus t sub 2 plus t sub 3 plus t all up to t sub n. And the recursive definition is basically that S sub 0 means you haven't added anything up yet, so that's 0. But here's the recursive idea. S sub 1 is just going to be t1. S sub 2 is t1 plus t2. S sub 3 equals t1 plus t2 plus t3. S sub 4, now this is getting tedious, so what you can do is to say S sub 4 is S sub 3, all of this, plus t sub 4. So that's what we mean by S sub n is S sub n minus 1 plus t sub n, for n greater than or equal to 1. So to get the sum of the first n terms, you add up the sum of the first n minus 1 terms and add up the nth term onto that. This will come into play a lot more when we get into inductive proofs later on. Here's our first example. Find the sum of the cubes of the first 20 positive integers. So that's, by hand, 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed plus 6 cubed plus 7 cubed plus 8 cubed plus 9 cubed plus 10 cubed plus 11 cubed plus 12 cubed plus 13 cubed plus 14 cubed plus 15 cubed plus 16 cubed plus 17 cubed plus 18 cubed plus 19 cubed plus 20 cubed. I hope you're big on your cubes. Oh my gosh, that's a lot of work. Well, there's an easier way. I want you to learn how to do it on the calculator with just a simple sum key. This is the Greek letter sigma. It's the capital S in Greek. And you can find it in your catalog or in the F3 calc menu right on your home screen there, and option 4, sigma, and it actually puts a little sum there. So there's parts you have to put in. You have to put in a formula here, and since we're summing up cubes, our formula is n cubed. We have to put the index, so that's n in this case, and we go from 1 to 20. So n is going from 1 to 20, so that'll give us from 1 cubed up to 20 cubed. And when you do that, you get 44,100. That is a lot easier than going through all that. But I wanted you to see what's meant by when we do a series of a sum. Now, find the sum of the first 100 numbers, natural numbers, without a calculator. So you go 1 and 2 and 3 and 4 and 5 and up to 100. Now, I'm not going to do what I did before there. That's way too much. And you can see this would be a real pain by hand, but maybe some of you see a little pattern you can use here. And our friend Carl Friedrich Gauss came up with this when he was basically in primary school. Look at that, you take out the E there, you got our Dr. Bartle. There's one of Dr. Bartle's ancestors, was the assistant, and he was also astonished when Gauss came up with his answer, just in a matter of seconds. Well, how do you do it? Did you get an answer akin to a popular soft drink? I'll let you try it on your own. Okay, here's how you do it then. You pair up the numbers 1 with 100, 2 with 99, 3 with 98, 4 with 97. And by that clever pairing, we're going to get down to 50 and 51. So we're going to have 50 pairs, and each pair is 101 per pair. And so you get 5,050 or 50-50. That's the popular soft drink I was talking about over here. Now, we're also going to come up with a formula for this, so you don't have to look at this clever trick every time, but this trick is part of the proof of this. To find the sum of a finite arithmetic series, this is the formula, n times t sub 1 plus t sub n over 2. Do you see how it works in our last problem? n over 2 is basically we had 50 pairs. We had 100 numbers and we paired them up, so we had 50 pairs. And the first number, 1, and the last number, 100, always made that sum of 100. And you're going to keep getting that sum if you go to the second term and the second to the last term. So here's the proof. We can write the sum formula twice. Basically, the sum of the first n terms is t sub 1 plus t sub 2, which is t sub 1 plus 1 common difference. And t sub 3 here, this is t sub 2. T sub 3 is t sub 1 plus 2 common differences, and so forth till we get to t sub n. And now we write the same thing backwards now, starting with t sub n, and we're going to write backwards. To get to the t sub n minus 1 term, you have to subtract d. So when you add up these two expressions, you get two equations, you get 2 s sub n equals t sub 1 plus t sub n, that's the sum of these two, plus, I'm going to add up these two, and notice how the d and negative e cancel out, and I get t sub 1 plus t sub n again, plus, and now I'm going to add up these two, and notice the 2d and negative 2d cancel out, and I get t sub 1 plus t sub n again, plus dot 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 dot, and finally we end up with adding up these two, and we get t sub 1 n plus t sub 1, or t sub 1 plus t sub n again. And we get the same thing on these last two as well, t sub 1 plus t sub n. So how many of these do we have? Well, we're going to have n of them. So 2s sub n equals n of these t sub 1 plus t sub n's, because we went from t sub 1 up to t sub n. And so s sub n equals n times t sub 1 plus t sub n over 2. Now you got to be careful, because in the Gauss problem there were 100 terms and t sub n was 100, but don't get the impression that those are the same. It was only the same in this case because we did the identity function where you're just counting 1, 2, 3, 4, 5, 6 and so forth. T sub n and n in general can be very different from each other, as we see in this problem. Find the sum of the first 25 terms of the arithmetic series. So first we've got to find the 25th term to use our formula. So that is t sub n equals t sub 1 plus n minus 1 times d. So t sub 25, the 25th term, will be the first term, 11, plus n is 25 minus 1 times d, and the common difference here is 3. Everybody see the common difference there? We keep going up by 3. So that's 11 plus 24 times 3. 11 plus 72 is 83. So the 25th term is 83. Now, use the s sub n formula. Well, s sub n is n times t sub 1 plus t sub n all over 2. So s sub 25 is 25 times t sub 1 plus t sub 25 all over 2. And this is the distinction I was talking about here. The difference between t sub n and n. We get 25 times t sub 1, which is 11, plus t sub 25, which is 83, all over 2. So we get 25 times 94 over 2. So that's 25 times 94 divided by 2 is 47. And when you multiply that in your calculator, you get, oops, one. Let's get the one that works. 25 times 47, and I'm coming up with 1175. Now, we just used this formula, s sub n equals, n t sub 1 plus t sub n over 2. But there's an alternate formula that you can get by making this substitution, by putting in t sub 1 plus n minus 1 times d in for t sub n. You end up with this formula, n times 2t sub 1 plus n minus 1 times d all over 2. And the advantage of this is that you save a step. So when we do the sum of the first 25, we can say 25 times 2 times t sub 1, which was 11, plus 25 minus 1 times d, which is 3, all over 2. And let's simplify that on the calculator. And again, we get 1175. All right, now sums of finite geometric series. Well, you got a couple alternate formulas here, and there's a nice proof in the book. You can check that I want you to kind of see what the results is and why we sometimes talk about the common ratio, where r equals the common ratio, get that n out of there, and r is not equal to 1. S sub n is t sub 1 times 1 minus r to the n over 1 minus r. Now if you distribute the t sub 1, you get t sub 1 times r to the n, which is t sub 1 times r to the n minus 1 times r, and t sub 1 times r to the n minus 1 is t sub n. So that's where I'm getting this r times t sub n. This alternate form is sometimes useful in the cases where you don't know the number of terms, where someone just tells you the first and last term, and you still know the common ratio. This form is useful if someone tells you the first term, and you know the common ratio, and you know the number of terms. So note the distinction there again between n and t sub n. Now why can't r equal 1? Well, r equals 1 would lead to division by 0. And the division by 0 is undefined. Undefined. Well, what if r equals 1? Well, if r equals 1, then your sequence becomes t sub 1, t sub 1, t sub 1, because you keep multiplying by 1. And so it never gets any bigger. So the formula then, just for the sum of the first n, would be n t sub 1s. So you could use that formula for the case where r equals 1. You really don't have much of a geometric sequence. Technically it is, because the common ratio is 1, but you can just multiply by the number of terms of the sequence times the first term. Here's our example 4. Find the sum of the first 10 terms of this geometric series. So we substitute in. Now which one are we going to pick here? Well, we know the first term. We can figure out the common ratio, and that's negative 6 over 2, so that's negative 3. We have to find the first 10 terms, so that's actually giving us what? Not the 10th term, but the number of terms, that n equals 10. So we could find the 10th term by expanding this all up, but I think this formula is best fit to the information we have. So the sum of the first 10 terms is t sub 1, which is 2, times 1 minus the common ratio, which is negative 3, to the n, which is 10, all over 1 minus the common ratio, which is negative 3. So this is twice 1 minus, and the negative to the 10th will cancel out, and we get 3 to the 10th. We can do that on the calculator. In fact, you do the whole thing on the calculator if you show me what you're putting in. We get 59,049 all over 4. So that part reduces, and we get division by 2. And we get 1 minus, so we get negative 59,048 divided by 2. Negative 59,048 divided by 2. And you end up with negative 29,524. And now we can check this on the TI-89 with that sum thing again. Now, what you're not given, though, is you would have to come up with this idea for t sub n in a geometric. Remember, that's t sub 1 times r to the n minus 1. So in this case, that's t sub 1, which is 2, times negative 3 raised to the n minus 1 power. And that's what I'm doing here. And so that's how you can check it on your TI-89. Okay, flange out.